we do today, we study the continuous random variable, which is quite the opposite of the discrete case that we spent the last 2 weeks on. So we define first and then introduce what's necessary to cover those stuff. So we define the variable as a real valued function that maps all over events in the sample space onto real line. So one way to classify those so-called random variables is whether the values taken by the variable is discrete or continuous. So if you can count them, whether it's finite or infinite, we say that as a discrete random variable, like integers. But somehow, if you cannot count it, if the value taken by the variable cannot be counted, we call that one as a continuous. Many examples, continuum of real numbers is the easiest example that we can find in real life. So for example, we can define random variable to be a time that a certain train arrives at a specified stop. So that one is certainly continuous because you cannot count them. You can say those the boundaries like between 0 and maybe 100, but there's no way you can count those possible values taken by this one because it's a continuum of real numbers. If you say that the time could start from 0 all the way to 100, whether the unit could be minute or hour. So there's certainly some value in this the interval, but you cannot count it because once you count this specific point, there's a nothing comes right after this one. You can always find something in the middle of those two choices. So in that sense, it's not countable. Another example could include like a lifetime of certain machine, the transistor. You know what transistor is. So that could be an example of continuous random variable. So anything that we can define this way, there are certain real values, numbers taken by some random variable, but you cannot count them. The potential outcomes, choices. You call that as a continuous random variable, which is quite the opposite of the discrete case that we did last time. So official definition of this type of variable is this one. You say that a certain variable is a continuous and random if there exists some non-negative function f. So we introduce another function f defined such that for any real number between negative infinity and positive infinity, having the following property. So as long as you can find such a function, little f, you call this underlying variable x as continuous. And this equality strictly says that assume that this x takes the whatever value might be covered by this set b, and this probability can be easily computed by integrating this underlying function little f over this area, whatever that is. We call that as a b in this case. So if you imagine certain non-negative function, so there's a real line. Argument of this function could be x. Non-negative in the sense that that stays mostly above this horizontal one. To call that as f. And if you want to figure out the probability that this x belongs to a certain range, could be like a negative a, positive a, call this range as like a b. Same b that we see over here, so this b. Area under this curve f is nothing but the integral of this real valued function such that the computed number represents the area under the curve between these two endpoints, -1 to a, and that one is nothing but the probability such that this variable a belongs to this interval or set b. So if you can find such a function f, we call that as the probability density function. And then this x is called the continuous random variable. So the two things together. First, find certain function f. You either find it or given by the question. And this f must satisfy this equality. If you want to figure out the probability such that this a belongs to set a, set of certain events, and this probability can be computed using this f such that you integrate this function over this area b, and then you get this probability. So once this one is satisfied, we call this integrand little f as a probability density function, And then this x is called a continuous. We'll be back again and again, so better familiarize yourself with this one now. So f is called the probability density function. You all remember what it was called under the discrete case, so called the probability mass function, PMF. Something like that, but not exactly the same. In the discrete case, we just list the possible values taken by this x. So x could be like any positive integer, like 1, 2, and 3, all the way. So there's certain probability here, another probability for the second choice, other number for this third outcome. You can just list these different probabilities, and that function is called the probability mass function. Something like that in the continuous case is called this probability density function. So this f is something like that in the discrete case, but in the continuous case, you cannot count them. But in this case, you can literally count it, 1, 2, and 3, and 4, but you cannot possibly count them in the continuous case. So in the continuous case, we cannot possibly write distribution function this way, or rather use that kind of notation. Integrand of that integral, little f is some real value function. That one is called the probability density function. And even the part of the name changes from mass to density, although the function stays exactly the same. So we used to call that as probability mass function. And then listed all those corresponding probabilities under those different values taken by x. But we cannot do it in the continuous case because it's a continual real numbers. You cannot possibly count them. So you have to specify a certain function, and this function must satisfy this equality. Probability density function, simply abbreviated as PDF. Just the same way we call the probability mass function as PMF. So we call that as a P dot D dot F dot. So that's a simple abbreviation. Right? Let me know if it's not clear. I'll explain again. So if you find this one difficult understanding, think of the discrete case first. So if a random variable is discrete random variable x is supposed to take some finite or infinite number of discrete values, integers. And then for that one, you can come up with a table like this one, which is called the PMF. So probability like this, table for probability like this one is called the probability mass function. Right? It's a probability mass function because it lists all those possible probabilities under these different values. So you cannot do that in the continuous case because it's a continual real numbers. You cannot count them. Here we can count it. First one, second one, and the third one. But if it's just the interval real continual numbers, you cannot count them. So you cannot specify the distribution under this table. You have to come with the alternative way, and that alternative way is this one. Define this function f, which is something like this function, but not exactly the same way. Then if you integrate this function over this certain range, and that number, integration will deliver you the probability such that this x belongs to the same interval range, B. So that's a probability density function. To differentiate it from the discrete case, we call that as a density function. So what's the primary usage of this function? Simple, given by this equal, you want to compute this probability. That's why you use it. So probability of event is basically the ultimate goal in this class. You want to figure out what's the specific probability for such an event, such an outcome will actually occur. And that one is computed using this integrand, which is a density function. In the case of discrete random variable, the way you figure out this probability, you simply go back to a table like that one, and then figure out what are those corresponding probabilities and mostly sum them up. But that cannot be done because it's a continuous case, so you have to go through this integration. So first define it. Either you find it, but mostly will be given by the question. Given this function f, you just solve up this integration, and the reason is because you want to figure out this corresponding probability such that x belongs to this set B. That's why. Mostly. Some other reasons you see. as this class moves along, but at the moment that's mostly the right reason why we want to or ever want to figure out this f and then figure out this computation. Okay? So in different way to deliver the message, clarify the meaning of this probability density function and the corresponding random variable might help you if you look at the whole thing this way. So the probability that x, real valued random variable, belongs to this interval, that's a valid interval, basically real line, is always 1. That one, you just agree. No other way you can specify this x. Either bigger or equal than the left hand, or either equal to or less than the right hand, always must happen because this one is complete set. But first one is just the common sense. As long as this x is a real one, probability that x will be on the real line is always 1. So putting these two different equalities together, we easily figure out this minimum requirement for this valid PDF, such that if you integrate any valid PDF over the real line, you must obtain this number 1. Otherwise, you know that there's something wrong with this f. So similar way, back in the discrete case, you first propose certain probability mass function, something like that. And if you want to figure out this one was well constructed, simple way to check it, sum these values over all possible x, whatever the number could be, say n, and this one must add up to 1. We used to do it. Right? So first propose this probability mass function, and then sum up these values under which all these potential x is taken by this big X, and this sum must be 1 if this P is the valid PMF. Something similar happens there. If you want to make sure that the proposed probability density function is a valid one, this time you integrate instead of doing summation, and then make sure they come up with this entity, no, not entity, unity, 1. So what's the ultimate goal of this proposing so-called probability density function and everything? Simple. You want to figure out certain probability involving this the defined x. So one example could be this x could be bounded by this some real number a, another real number b, and that one can be figured out by using this f and then doing this simple computation over the range between a and b using this probability density function. Right. So first define this f in a proper way such that if you integrate it over the entire real line, you make sure that you obtain 1. And once this is checked, once you sure that this is a valid PDF, you just use it in practice. And the typical usage of this proposed function is to computing probability like this one, involving the underlying variable x. So after you are here to compute certain probabilities. That way it can be, this one can be done using so-called probability density function in the continuous case, as opposed to the discrete one. If you try examples, things will look clearer. Before we try some examples, a few more comments about the characteristics of probability density function. By the simple theorem of this calculus, fundamental theorem of calculus, any probability for continuous random variable take one specific one value, like a little a, always 0. Always. So computing the probability for intervals like this one is one thing, and computing the probability that x is exact equality, so it's exactly the same as some number, some real number a, that's quite different. But if you stick with this definition of how to compute this probability using some continuous random variable, you always compute it this way. But then the fact that x equals a basically means that each endpoint, the previous equality is exactly the same. So if you make this a and b some same number, equal ones, that's nothing but this. But then by making the bottom end, which is a, top and here b, but here we assume that a and b are the same, then if you equating the top part and bottom part here, doesn't matter what you integrate over, the integrand is always 0. Why is it 0? So how come this integral is 0? You know what integration is, right? You learned it back in high school. Raise your hand if you haven't heard such a thing before. Let me know if this is your first time to see a symbol like this one. Can I highlight it? You know what this one says? So why is it 0? If you make the bottom end and top end same number here, the resulting integration of this function over this range, well, it's not a range, it's just a specific point because it's just a 1, is always 0. Why? Anyone? What does the integration do? Graphically? So you propose certain function here. If you integrate this not f, between negative a and a, so make the bottom one as negative a, and then put a at the top. What does this one represent? What is this? What's the primary purpose using integration in mathematics? So the opposite of this operation is differentiation, which is called df dx. What's the primary usage of this one? You want to figure out the change rate, because if you control this x, the value taken by this f will change. We just want to how fast does it change. That one is done by that. But what's the primary usage of this integration? You want to compute the area. You want to compute area under f over. So that's the primary usage. You want to figure out what the area under this curve between this negative a and a. But what happens if you make those each end, both ends same? So you are not integrating between negative a to a, but you are integrating between a and a. And how do you represent, using this picture, what we are computing here? If you make this one as both a here and there, that's the area of this line. Right? Because you are starting at A, but end at A, which means that you don't move at all. So what you are actually computing is the area of this line. What's the area of line? So 0. Why is it 0? Standard textbook and go to the theorem called the fundamental theorem of calculus. That's what it says. The area should be 0. For any straight or curve. What made you argue that? Think of a rectangle. You know what a rectangle is? So there are two different sides, the bottom one and this vertical one. And the way to compute the area of this rectangle is a times b. But if you make a line, b might be still there, but a is basically 0. So if you multiply anything by 0, that's a 0. So that's why. So the key point is that any valid PDF of any continuous random variable, say f, if you integrate that one over a certain specific point between a and then the same a, that's always 0 by the fundamental theorem of calculus. In other words, the probability such that this a takes on specific number a, it always happens with probability 0, which means it never happens. Okay? So in different way to put the basically same thing. You first compute the probability such that x is either equal to or less than a. That's one event. And you might also want to delete this equality out of it. So you just want to make it strictly less than a. So those are two different things. But whether you compute the probability for this second outcome or the first one, that's essentially the same because of this. Probability that any continuous random variable takes on specific one real number is always nothing. So it doesn't matter whether you include this case or not. Here you don't include it. Here you include it. But there's no difference between these two because the probability mass over the specific a is always 0. Questions? Wait, do we have questions? I'm talking to you. If you have questions, ask me, not your friend. That's why I'm here. So it doesn't really matter whether you include this equality or not. It's always the same thing. We'll formally introduce the uppercase f later. This is called a cumulative distribution function. The same kind of cumulative distribution function they used in the discrete case. This one is used as a compact way to represent this probability. Make the bottom end of this integral as like the smallest one, which is negative infinity. You raise it all the way to up to some other number a, but this one just simply you write it as a big F. If you put this a into argument of this function, this one is going to represent this integral. But this one is another thing which we will discuss further later. Now we try some examples, see how it works in practice. So typical quiz or exam questions might start with something like this one. So present only partial result, partial identification for this density function, probability density function, PDF of some continuous random variable x. So here it's defined to be for two different cases. If x is strictly between 0 and 2, equalities are not included. Has to be either bigger than or less than. But then corresponding density function, some unknown constant c times 4 times x minus 2 squared is basically 4. Otherwise, there's no probability mass. So that's a PDF, density function. The question has two different parts. First, the determine the value for c, which is the unknown coefficient, and then figure out this corresponding probability for other outcome, other event. X is strictly bigger than 1. So necessarily have to figure out what the value for c is first, and then we can compute this corresponding probability. We can do it now to figure out what the c is. How do we compute c first? Spend like a minute or so to think about how we can get c, and then we can do it together. Of course, you want to make this one as a valid PDF, so you can use this property here to figure out what the c is. If you integrate this PDF over the real line, you must add up to the integration must be 1. Otherwise, that's not a good one. But you want to make this one as a valid PDF. Otherwise, there's no way you can compute this probability. So make sure that this PDF is okay. It's a legitimate one. And once you make sure that by picking up the right number for this C, then go to the second part and compute this corresponding probability. Right? Homework 3 is longer than the previous two. So this time I actually might directly use one of those questions for the quiz to make sure that you actually did it. I write it this afternoon. I haven't written it yet, but that's one thought. The last two homeworks were rather short, so it's quite unfair to just exactly copy one of those questions and put it on the quiz, but not for this one because this one's pretty long. Yeah, just try each one of those and make sure they understand that. Instead of one full day. So let's do it. First is first. The number for this C. So because of this property of this PDF, if you integrate the PDF over the entire real line, it must add up to 1. Otherwise, it's not a good PDF. So the way to do it, just put this C outside this integral because it's a constant, and then figure out what's this integrand for this remaining part, and then move it to the left-hand side, and this will give you this number 3 over 8. You know how to handle this one, right? You do. Because it will be on the quiz and exams and everywhere. If you don't know how to do this one, let me know. But if you don't say anything, I'll just assume that you know how to handle it. Yeah. But once we figure out the number for this C, the rest of them is easy. Just use the specified, identified PDF down here, but then only you need to specify what the range is. Range should be bigger than 1 and can be anything above that. So using this the identified PDF, you go ahead and solve out this second integration, which is this integrand between 1 and 2. And then you compute, figure out the answer is nothing but half. And in case you are not familiar with this integration operation, so despite this type of integration is application of nothing more than this. That's pretty much it. All you need to know to handle it. It's quite the opposite of differentiation. If it's a differentiation in terms of this base, you take this power exponent down and then subtract it. But that's the case of differentiation. If you do the integration, you do the opposite. First add it, and then divide it, and then raise power by 1, exponent by 1. Second example, with a personal computer, it's supposed to function some hours without any problem, and finally breaks down. So the lifetime of this computer, PC, can be modeled as a continuous random variable, and its lifetime is x. So that's this random variable x. And then the ensuing probability density function of this x can be specified like this one, function like this one. Some unknown constant lambda, and there's an exponential function, the same type of exponential function that we introduced last time. The exponent of negative x over 100, since it's a lifetime, it has to be always non-negative. And of course, the opposite case, when the lifetime is negative, so of course, never happens. Probability 0. Given that, you want to figure out, compute the probability such that this PC, this personal computer, will go okay without any problem between 50 and 150 hours before it breaks down finally. And then subsequently, you also want to figure out what's the probability that this one will remain okay, functions well for less than 100 hours. So those are two different events. One is the lifetime of this computer bounded by 50 and 150, and second case is way less than 100. So those are two different events, so probability should be different. You just go for each one of them and then figure out what's the corresponding number for each. Try now, and again we compare the answers. So since this coefficient lambda is not known, just like the previous case here, so C was not known, so you have to figure out what the number for C is first, and then compute this probability. Same type of strategy can be applied here. So part of this probability answer function is not identified. So first figure out what the value for lambda is, and then go for these two different probabilities for different events. That's the way to do it. So first go for the lambda and figure out what this one is. And for this type of work, formula that you might want to keep in mind. A is some number. If you get confused about this integration operation, always think about the differentiation first. So if you differentiate e to the a times x, that's the base stays exactly the same. Just have to integrate this part, which is the a, and then you are just moving backward. That's how come you have to inverse this a. So that's the case of integration or differentiation. And then you're moving backward. Right? If you divide this one by a and this one by a, you get that. So moving this way is differentiation, but if you move the opposite, so from right to left, this one is integration. You know how come you have this coefficient a here, right? So chain rule, because this exponent is another function of x, so you have to differentiate that part too. So it's called a chain rule. So always first figure out, if you get confused about this integration, first figure out the differentiation first and then go back. So that way you can make sure that you don't get lost or get confused or anything. So if you do this one, so first the number for this lambda. So first solve out this one. So if you integrate it, the given partial PDF over the entire positive real numbers, that's 1 because that's a PDF. So first solve out this integration, and then you get that. Here the a is a -1/100. The general formula is this one. So if you set this a to be negative 1 over 100, you get the same thing. So plug in the number, this number here and there, and then you get the integration of the PDF function. So that's this, but of course the lambda follows because it's just a multiple. First plug in this positive infinity into this x, and this one will give you, what do you get if you plug in infinity into this x? Huh? You know this notation, right? So definite integral something like that, right? First figure out the integrand, so little f. Once you integrate it, that becomes the big F. So raise it to the uppercase, and running from lower end to top end. First to substitute the upper end first, and then low end, and then get the difference. You haven't seen this one before? Who have seen something like this one before? You have? You did? Yes or no? Yes. Who else? You never done the definite integral before? Well, this type of general form is called the indefinite integral. And the relation between this integrand and then this result, if you differentiate this one, you get little f. So these two relationships is called the fundamental result of fundamental theorem of calculus. Right? Only need to do this basically. So definite integral is just a specific case of this indefinite integral. Indefinite in the sense that you have to integrate over that real line. But if you specify lower end to be A and then bottom end to be B, first apply this first half of the fundamental theorem of calculus, figure out what this function is, and then running from A to B basically means that first substitute the top end to this function first, which is f of b, and then subtract the same function when it's evaluated at this bottom end, which is f of a. So that's what is called the fundamental theorem of calculus. Differentiation you must have done. You probably may not have seen the opposite case, but this one you must have done it before. But specifying this the unknown lambda require for us to figure out this definite integral. You first apply the fundamental theorem calculus and figure out what's the indefinite integral first, and that's this. So that's like a big F in this case. So that's like that. Then evaluate that big F. First at the positive infinity, and then 0. So my question was, what happened to this integrand result if you evaluate this highlighted part at positive infinity. So in other words, if you plug this positive infinity into this x, what do you get? What's the value of this function if you evaluate the entire thing at this number? So first think about this one. What happens if you plug in positive infinity into this x? So this one slash means division. Right. So that's what I mean by this negative. You have to take the inverse of it. But if you plug x infinity into this x, the bottom one is just infinity. So if you divide any finite number by infinity, that's 0. Okay? But what happens if you plug in 0 into x? This one should be easy. 1. So that's why you get 100 times lambda, because you're subtracting it. So if you go through detail, first you evaluate that one as if you first plug this one into x, you get 0. And then you have to subtract it. You subtract it. And the value that you are subtracting is this function. When you evaluate the whole thing at this bottom part, bottom end, that's a 0. But if you plug 0 into this one, the whole thing becomes 1. You just have a negative lambda times 100. We have two different negatives. First subtract this one, but there's another negative in front of this one. It's the same thing as adding 100 times lambda. So that's why you're having this. Okay. So the correct value for this lambda is a 1/100. Right? So identification part is done. You now have fully specified this underlying PDF, and then you go to the probabilities of those two different outcomes that you ultimately want to figure out the probability for. So first one, lifetime of this PC at minimum 50. It's bigger, but at most is a 150, but no longer or more than 150 hours from this starting of this operation. Using this value for lambda, complete the identified probability density function is this one. Right? Go back to the probability density function. Now lambda is figured out to be 1/100. If you just write it down, that's this. Now you integrate it, this fully identified probability density function between 50, 150. First, integrate the indefinite integral, and that's this. And then you evaluate the same function first at 150, and then subtract the function when you check it at this bottom end, which is 50. And then the difference, first one should be e to the negative half, and second one turns out to be e to the negative 3/2, and difference is approximately 0.38 and 4. So it's a two-step. First, figure out this value for lambda, and then go to the probability, computation of this probability, and you get this. Second step, basically same operation, except for the fact that you have to switch this, change the two ends from 50 and 150 to 0 and 100, but then the rest of them stays the same as before. So integrand fully identified PDF, and first do the indefinite integral of that PDF, and you get this, which is the same as before. Then just that you need to plug in different numbers this time because the range is completely different now. So first plug in this 100 into x, you get to, what do you get? Something wrong here. Oh, yeah, yeah. So what's happening here? So first plug in the top end, which is 100. So what you're having is so first plug this top end into this the integration, indefinite integral. You get this minus subtract the same function when you plug this 0 into x. That's this. But then this one is 1, right? But you have a double minus, so it's basically plus. So you're switching the order basically. This one becomes -1, so you put this one first, and then this one comes down here. So that's why you're having 1 minus e to the -1. Because you swap the positions of those two numbers. If you compute this one, that one turns out to be a bit higher, bigger than the first one, so 0.633. Make sure that you can operate these things without much difficulty because we'll certainly be tested one way or another. Questions so far? Just need to understand two things, fundamental theorem calculus and those basic property of the PDF. Then all others, just the application of those two, one way or another. Third example. This one. This one's interesting. Keep talking about either computer or radio tube. So there's a lifetime in hours of certain kind of radio tube, some kind of like a parts in radio. It's a random variable, but this is a continuous, not discrete. So we have to define some probability density function, not mass function. And PDF takes this form. Chances that this radio tube will operate less than 100 hours is nothing. Never happens. At minimum, it operates without any problem for first 100 hours. But after that, the lifetime diminishes rather quickly. And that one is governed by this rule, 100 over x squared. And x is the lifetime of this radio tube. And at minimum, this is 100 or bigger. But how far it will go depends on this probability. So if x becomes extremely large number, since we have to divide 100 by the square value for that x, and this probability will be tiny, which means that that's unlikely, which makes sense. But given that, what you want to figure out is this one. There's a random choice of 5 such radio tubes out of many other radio tubes that are generated or produced by this company. Exactly 2 out of these 5 so such radio tubes, would have to be replaced within the first 150 hours of operation, which means that lifetime is less than that. So we're talking about only 2 out of 5, not just indefinite number of such radio tubes. Random pick, 5 picks out of many other radio tubes manufactured by this company. Only exactly 2 out of such 5 will stop working within the first 150 hours since it started operating. We want to go for this probability. That's what this question is asking. Where will you start? I think this one I used it for some exams. I forgot the exact number, year. But this one was the actual exact question from past year. So PDF is given. It's a complete identified PDF. And if you indeed integrate this one, so if you want to make sure that this is valid PDF, you gotta integrate this one between 100 and infinity. You indeed get 1, so this is okay to use. But you use it to compute this probability. So exactly 2 out of such 5 random radio tubes picked randomly. So lifetime for those 2 will be at most 150 hours. So if you see this part, first part, exactly 2 out of 5, this one sounds familiar. We tried many such situations before, but if you see expressions like this one, you automatically think of what kind of random variable? Binomial. You have to repeat it like a finite number of same sort of things with exactly the same probability for each. But then it's just more than that because you have to involve this continuous random variable too. So it's not only binomial, but also that has to involve this continuous random variable with this specific PDF. So which one should be identified first? Binomial part or this continuous one? So as always, computation of some probabilities start with the definition of some random variable. So define proper random variable in the proper way, and this is no exception. So we can let xi be you have to deal with like 5 different radio tubes in this case. So come up with certain index like I, and then define x sub I. So there's I to differentiate those different lifetimes of different radio tubes. It's nothing but a lifetime of that radio tube, the ith one. Could be first one, could be second one, could be third, maybe fourth, or possibly the last one, the fifth. And I is obviously running from 1 through 5. Okay? So I can be 1 through 5. Because there are 5 different radio tubes. So you want to figure out first the following. Because that's the second half. We have to replace within the first 150 hours. So this probability, such as xi, either equal to or less than 150, represents this highlighted part. Have to replace within the first 50 hours means that the lifetime is less than that. How do you get this one? Simple. You have the PDF, which is that one. what's this? How can you simplify this integral? So since lifetime cannot be negative, obviously the bottom end should be 0. But there's a way to simplify this one in this case. You can make this range to be, the low end could be not clear. Divide into two cases. Okay, that's easy. Break it into two parts. Well, what's the first integral? This is actually not exact. You have to put that as a general notation here. Oh, wait. It should be 100. Because anything less than 100 will equal to the corresponding PDF is 0. So first one, you don't have to evaluate it, that's a 0 itself. You only need to compute this second half. Okay. Here they use the E. So if you first compute this probability and combine that with the binomial thing, the official solution for this one should be something like this. So define EI so to be that XI is either equal to or less than 150. So using the given provided PDF of this X, supposed to figure out what the value for this integration is. But then the knocking off the first half, running from 0 to 100 because the integral is 0, given by this question itself, you only need to evaluate the second half when X is running from 100 to 150. And if you do the computation correct, and that probability is 1/3. So any random one out of those 5, the event such that the lifetime of the radio tube, less than or equal to 150 is a 1/3. But you have a binomial random variable at the same time. You have a 5 of them, not just one of them. But then you want to make that only 2 out of those 5 will fit into such a case that the lifetime is less than 150 hours. So that's nothing but 5 choose 2 with a success probability of this 1/3. So the first half of this question is nothing but the figuring out the success probability. So that's a 1/3, and that only happens twice out of 5. Rest of them, failure. Repeat it 3 times. So final answer should be 80/243 if you do the computation correct. So always first define whatever the random variable you need to figure out whatever for. First define that first. And here is the lifetime of this light tube, radio tube, not light tube. Could be like an X or could be E. But then first figure out in this case success probability, that because it's a binomial case. And once you figure out the success probability, which is 1/3, and go to the usual binomial case. So that's 5 number of trials, number of successes, you need to be only 2. 5 choose 2. So repeat it with this computed success probability 1/3. The rest of them is all failure. 1 minus success probability, which is 2/3, and then you just repeat it 3 more times, and that's the entire thing. The eventual probability you need to figure out. And some other applications can be easily cooked up, but the way to handle this stays the same. First, go for this definition of x, figure out the success probability, and then finally try this binomial distribution to figure out the probability that's being asked by the question. Questions or comments or anything that I can? Cumulative distribution function, well, at least we can do it now, but the expectation we'll study tomorrow. So given this PDF, you can easily define so-called CDF, which refers to this cumulative distribution function, which comes on the next page. So this one name-wise the same, no change between the discrete case and this continuous one. Notation even stays exactly the same, uppercase F. So if you define F as certain real value A, that's nothing but the probability that the corresponding random variable for this CDF, say X, so either equal to or less than this right end, which is A, and then that one can be computed using the same PDF. So relation between this CDF is cumulative, so only you have this right end point. Left hand is always a negative infinity in the case of continuous random variable. So bounded by this A, so using the definition under this defined PDF thing, that's nothing but this integral running from lower end, which is negative infinity in this case, to the upper end, which is a finite number A. And the integrand is this PDF. And then if you compute this integral, it's nothing but this probability. And this probability is called the CDF of this X when you evaluate the whole function at this upper end, little a. And by the fundamental theorem of calculus, if you differentiate both ends, you are supposed to get this PDF back. So relation between this PDF and CDF, so lower end, the lowercase f is a PDF, uppercase is a CDF, which is defined here. If you differentiate it, you get the PDF, but if you integrate it, you get the CDF. In a continuous case. Right? And that's what's being said down here. So that's basically moving from here to there. So if you integrate it, you get the CDF. If you differentiate, you get the PDF. So once we introduce the PDF, the introduction of CDF is very trivial because it's nothing but the integration of the early defined, introduced this probability density function. And the result of that integration is called a CDF. Cumulative. Cumulative in the sense that the left hand is always this negative infinity. You accumulate this probability all the way up to this finite number A. So in that sense, it's cumulative because there's no left hand. It's just open. So here it's written there. It's written that way. But the more easier way to write it is basically this. Right. So whether you write this or that, those two things are the same. Cumulative in the sense that there's no left hand. It's completely open. Only you're running up to this A. So accumulate this value under X all the way up to this A. In that sense, that's a cumulative CDF. clear? I think I'll stop here if you have, unless you have other questions. So quiz tomorrow when you come back, save the last 15 minutes of the class time. So we do the lecture about an hour, and then do the quiz. So the week after that, we'll do the review for the midterm. Thank you.